In this video, we are going to discuss about damped oscillations. Damped oscillations and its types. So let us start with the simple harmonic oscillator. Let us first consider spring mass system. So suppose this is a spring having spring constant K, and we have attached a mass M to it. So this simple harmonic motion we have studied before, and we know here the forces acting in this system is basically the inertial force, which is given by mass into acceleration of the system, and another force is acting here, which is called a restoring force. And that restoring force is always trying to keep that mass to the equilibrium position. So I'll write the forces here. The first force is a restoring force. Restoring force, which is equal to minus k times x, where this k is the spring constants and x is the displacement from the mean position. And the inertial force is given by mass into acceleration. So acceleration is second derivative of displacement, so it is d2x upon dt square. So what we get here by force balancing is the differential equation for simple spring mass system. So if we equate this particular force and do force balance, we get m d2x upon dt square, which is inertial force, is equals to minus kx, which is restoring force. And this leads to m d2x upon dt square plus kx equals to 0. And if you divide this particular differential equation by mass m, obviously mass not being 0, we get a simple differential equation d2x upon dt square plus k over m times x equals to 0. And we know this term. So this k upon m is nothing but omega square, where this omega is called the natural frequency of this harmonic oscillator. So we can write this differential equation in other form as d2x upon dt square plus I will write omega naught for frequency, natural frequency, square times x equals to 0, where this omega naught square is equals to k over m. So we know this. So now we're going to study what happens with the damped oscillations. So what happens? Suppose if I add here a simple damper. So what is meant by damper? The damper is generally represented by this. Suppose this damping constant is B. So damper is what? Damper is basically used to reduce the amplitudes of this vibration. Suppose if I plot displacement versus time graph for this x versus t for this particular spring mass system without damping, so it will keep oscillating between same amplitudes plus a and minus a. So it will be either sinusoidal, or it will be having cosine function, or it will be having certain phase angle, initial phase angle, right? So this amplitude will never decrease because we don't have any resisting force in this particular system. So this would be plus a and this would be minus a. And we know the solution of this particular differential equation. X is equals to, you can write a sine this omega naught t plus some initial angle, let's say delta. So this is initial phase angle delta. So we know this amplitude a, this sine function is periodic in nature, which will oscillate between +1 and -1. So multiplying by 8 will give us the sinusoidal curve, which is oscillating between upper limit plus a and lower limit minus a. So in short, in a nutshell, this amplitude is not going to be decreasing, right? So what happens if I add a damper here? So damper, what it does actually, it basically reduces the amplitude. This damper is for the reducing the amplitude. So let's discuss what happens if I add this damper here. Now, let us consider this system again, but now with, suppose this is spring with spring constant K, been attached with mass M, and now we have added this damper here, right? So this damper is going to damp out the oscillations, which means that it is going to decrease the amplitude of this oscillation. So, this damper offers a resistive force here. This resistive force, so this can be in terms of friction force, or it can be in terms of viscous force in terms of liquids. So this resistive force, which is being offered by this damper, is given by minus b times v, where this v is the velocity of this particular spring mass system. And this v, velocity, we can write this in terms of derivative of this displacement. So this damping force, this minus sign indicates that it is opposing in nature, which means that it is a kind of resistive force. And now, because of this additional resistive force, our amplitude is going to be decreasing, right? So if I write again the force balance, so there will be restoring force due to the spring constant, there will be inertial force due to this mass, and now there will be additional resistive force which is being offered by damper. So let's write the force balance equation here. So if I write force balance, this mass into acceleration, this is kind of inertial force, is equal to minus kx, this is restoring force, and minus b times v. So let us write this. This is actually inertial force. This is restoring force. And this is kind of resistive force. So this resistive force is an additional force. So that's why our energy is also going to be dissipative in nature, right? So because this amplitude is going to be decreasing and energy will definitely dissipate. And at the end, we'll have zero amplitude, which we call as a stable configuration, right? Suppose, for example, if you consider the simple pendulum, let us say this is stable position at theta equal to 0, where theta is the angle measured from the vertical. And now suppose if you displace from this vertical stable configuration a little bit, some small angle theta naught, and you release this bob, so it will keep oscillating, but not forever, right? So because though we consider, so you might have be remembering that while deriving this particular oscillations for the simple pendulum, you have not considered any kind of resistive force. But in practice, there is a resistive force which is being offered by air, and which can be in terms of air drag. So due to the presence of this resistive force in practice, we know these oscillations are going to die out after a certain amount of time. So that's what here the resistive force is, and that is being termed as the damped oscillations. So let us try to find the differential equation for this. So again, we write this inertial force as m d2x upon dt square, so equals to this minus kx minus b times dx by dt. So let's rearrange these terms again, d2x upon dt square. Now I'll write it as plus b times dx by dt plus kx equals to 0. Now, in spring mass system, we just had inertial term and restoring force. And now we have an additional term due to damper basically. So this term is b dx by dt. So again, if I divide this particular equation by mass m, so I get simple equation d2x upon dt square plus b over m times dx by dt plus, I'll just directly write k upon m, we already know omega naught square times x equals to 0. Now we have this additional term here. So for the sake of simplicity of the calculation, let's define this b over m as 2 lambda. Let us define like this, like, so our differential equation becomes d2x upon dt square plus 2 lambda times dx by dt plus omega naught square x equals to 0. Now I know if I solve this particular differential equation, I'll be able to get the displacement as a function of time t, right? So let us try to solve this differential equation. Okay. Now we have this differential equation here. So let's write this differential equation, d2x over dt square plus 2 lambda dx by dt. Remember this term lambda, which is equal to b over m plus omega naught square times x equals to 0. So let us assume, so let's not go into the details of the solving ordinary differential equation. So for the sake of understanding of how to get the solution of this differential equation, I'm just brushing up this particular thing, but it's like separate thing. It's like solving differential equation in particular. So let us assume the displacement as a form a e raised to alpha t. Okay, so let us solve for this. So let's find dx by dt. Dx by dt would be a times alpha e raised to alpha t. And if I find the second derivative d2x over dt square, it would be a alpha square e raised to alpha t. So if I put all these terms in this given differential equation, what I get here? So this implies A alpha square e raised to alpha t plus 2 lambda A alpha, this is e raised to alpha t plus omega naught square x is A e raised to alpha t equals to 0. So note this down. A e raised to alpha t, A e raised to alpha t, A e raised to alpha t. Let's take out that. A e raised to alpha t. What remains is alpha square plus 2 lambda times alpha plus omega naught square, which is equal to 0. So either of these terms has to be 0. So note down. The A e raised to alpha t is our solution. So this cannot be 0 all the time, right? So this factor which is mentioned in the bracket has to go to 0. So I write alpha square plus 2 lambda alpha plus omega naught square. This is equals to 0. And now we are supposed to solve this particular quadratic equation to get the value of alpha, because we know the value of lambda. Let me write this value here. Lambda is our b over m and omega naught square is our k over m. So we know the system. That's why we know the mass, spring constant, and this damping constant b, right? So let us solve this particular differential equation. By using formula method, we know the solution of this this quadratic equation. So alpha is equals to minus 2 lambda plus minus square root of b square. B square is our 4 lambda square minus 4 AC minus 4 omega naught square divided by 2a. Divided by 2 is our simply 2. So what we get here? So minus 2 lambda plus minus, take 4 square root of 4 common. So it would be 2 inside square root lambda square minus omega naught square over 2. So we have got the two values of alpha here. Let me write two values of alpha. The first one, alpha 1, which is equal to 2 common, take it out. So it would be minus alpha plus square root of, minus lambda plus square root of lambda square minus omega naught square. And the second value of alpha would be minus lambda minus square root of lambda square minus omega naught square. So these are the two values. If I put these two values here in this particular solution, I get the solution of the differential equation, and it will look like x of t equals to. Now, remember, this is a second order ordinary differential equation. So you have got two independent functions as a solution here. So you'll be having two constants. So first constant a e raised to alpha 1 times t plus b times e raised to alpha 2 times t. Because it is being second order ordinary differential equation, you'll end up having two linearly independent solutions. So your final solution of the differential equation will be linear combination of these two linearly independent solutions or functions, right? So write this down. So x of t would be a e raised to, this is minus lambda plus square root of lambda square minus omega naught square times t plus some other constant times e raised to minus lambda minus lambda square minus omega naught square times t. Now, depending on, so note this down here. So what this solution, basically the x of t displacement as a function of t, this entirely depends on this particular exponent here, the first one and the second one. So based on the values of this particular exponents, we are going to categorize these damped oscillations into three types. So let us see how. So note this down here. We have a square root of lambda square minus omega naught square. So we have three possibilities here. The first one, let me brief first and we'll go into details then. So the first one is obviously lambda square is less than omega naught square. So in that case, our this square root term becomes negative, and square root of negative term means it will go into complex, right? And if it goes into complex, exponential of complex number, by using Euler identity, we can write this in terms of cosine and sine functions. So we'll end up with the oscillations again, right? Second case. Second case is obviously lambda square equals to omega naught square. So in that case, this term will vanish, and look at the solution. A e raised to minus lambda times t plus b e raised to minus lambda times t. So this is kind of repeated solution. So we have a separate treatment in such cases, and will not only have this e raised to minus lambda times t, but there will be one more function which will be linearly independent of this solution. So that is again going back to the ordinary solution of ordinary differential equations. So let's not worry about that part right now. Let's go to the third case. The third case is lambda square, which will be greater than omega naught square. And this looks more comfortable, I think, right? So if lambda square is greater than omega naught square, okay, fine. This is a positive number. I can take the square root of this positive number, so there is no harm, right? So this looks like more comfortable to us. So let us discuss these three possibilities here. Okay, so the first one. So let us discuss the first one. Lambda square is less than omega naught square. So what we have here, let me write only one exponent here. So basically your alpha 1 value is minus lambda times plus square root of lambda square minus omega naught square, right? Now this square root, the term inside square root has become negative now, right? So this I can write as minus lambda plus square root of. So I can write this as minus 1 times omega naught square minus lambda square. Now I know omega naught square is greater than lambda square, so this term would be positive. And minus 1, I can write in terms of complex. So minus lambda plus I times omega naught square minus lambda square. So remember, in our solution, we have the terms like e raised to alpha 1 t and e raised to alpha 2 times t. So these terms lead to e raised to minus lambda. This would be either plus or minus. I will directly write this I times this omega naught square minus lambda square, right? So I can take this exponent separately. So this would be entirely times t. So this would be e raised to minus lambda times t into e raised to, let me write it as plus minus I square root of omega naught square minus lambda square times t. Now look at this term, particularly this term. So the solution, I'll just briefly mention as a solution. Solution will look like what? E raised to minus lambda times t. This term will be there. But as per identity, Euler's identity, e raised to I theta is cos of I theta plus I times sine of, cos of theta plus I times sine of theta, right? So using this particular identity, and again, so we are dealing in the domain of real numbers. So our displacement cannot be complex. So let's ignore this particular term. So e raised to, linear combination of e raised to plus minus I theta, I can write as a linear combination of cosine and sine. So in short, I can write this term as a combination of sine and cosine as sine of some omega t plus or minus whatever delta. And this is called underdamped oscillation. This is called underdamped oscillations. So the solution, the differential equation, solution of the differential equation for the underdamped solution will look like this. Some constant a e raised to minus lambda times t times sine of omega t plus delta. And this omega obviously depends on this particular thing because this would be the angle. So I theta. So this would look like this. This is our omega, right? The underlying term will be our omega. So this is called underdamped oscillation. So let's look at the condition again here. For the underdamped oscillation, our lambda square is less than omega naught square. So lambda, I'll write this here. Lambda is equals to b. This is 2 lambda is equals to b over m. So I might have written by mistake lambda equals to b over m in the last slide maybe. So correct it if I was wrong. 2 lambda equals to b over m. So lambda is b over 2m. So this is b square over 4m square. This is less than omega naught square, we know, k over m. So mass, let me cancel it. This gives me b square is less than 4mk. So for this condition, the oscillations are termed as underdamped oscillations. So why this like? So remember this B is a damper. right? So this is a damping coefficient, and this K is a spring constant, which will decide. So this B basically decides the damping force, and this K basically decides the restoring force. So what this condition basically indicates us? So this condition indicates that our damping force is less. So this damping force is very, very less, right? So obviously, because the damping, if the damping is very less, so it will keep oscillating, though it is going to decrease the amplitude, but it will keep oscillating. So if I look at the solution graph of x of t versus time, so suppose this is time axis. So suppose initially, if I plot from this limits plus a and this is minus a. So how to draw this graph again? So look at this term particularly. So this term is exponential of minus lambda times t, and this lambda, this b being positive, mass being positive, this lambda will be a positive number. So this minus of lambda t, this is basically a decaying term. So this is decaying with respect to time. So if I plot the exponentially decaying function, so it will look like this. And as time proceeds, it will go to 0 eventually, right? Again, if I start from this minus, it will eventually go to 0 as time proceeds. So it will look like this. So this basically represents a e raised to minus lambda t, and this basically represents minus a, because I'm starting from minus a, e raised to minus lambda times t. And now I have to combine this periodic function with it, right? So sine. So let's say, for the sake of convenience, let's take this initial phase angle to be 0. So our graph, let's say, starting from 0. So it will keep oscillating between these limits. So it will be looking like this. So look at the oscillations. So these oscillations, amplitude of these oscillations is decreasing with time, and it is also oscillating, right? So this is known as underdamped oscillation. So what is the best example of this underdamped oscillation? The best example of this underdamped oscillation is simple pendulum. So you know the simple pendulum, right? So here it is a bob. If you displace from the mean stable configuration, right, and release it from certain small angle theta naught, it will keep oscillating. But remember, as time proceeds, after a certain amount of time, it will eventually come to the rest, which is the stable configuration, which is an equilibrium position. So what it indicates? So we have started from the initial point of plus a, let's say. At the end of your experiment, you are at the mean position, stable configuration, right? So what it indicates, your amplitude has been decreasing throughout the course of experiment. So this is a kind of underdamped oscillation, and it takes more time, because here, as the amplitude is going to be decreasing in nature, so there has to be a damping force, which is a kind of resistive force, and this is being offered by air in terms of air drag. So this resistive force opposes the amplitude of this oscillation, and this amplitude will die out eventually, but after a certain long time duration. So this is what about underdamped oscillation. Remember the condition. The condition itself denotes that your damping, this damping is smaller as compared to the other forces in the system. That's why, because of slow damping, though your amplitude is going to decrease, but it will decrease at slow rates. And meanwhile, your system will keep oscillating, right? So this is called underdamped oscillation. So let's go to the next condition, which is called the second condition. We'll first see lambda square is now greater than omega naught square. Okay, so again, I will write the first one, alpha 1 equals to. Again, now from this condition, I can directly write from the previous slide, b square would be now greater than 4mk. This indicates what? Your damping force. Damping force is stronger now. Damping force is stronger than any other force in the system. So what happens here now? Now let me write the alpha 1 here. So this is minus lambda, let's say plus square root of lambda square minus omega naught square. And let me write alpha 2 as well, minus lambda minus square root of lambda square minus omega naught square. So look at these terms here. So this lambda square being greater than omega naught square, the term inside the square root would be positive. So there is no harm here, right? So let's not go into complex. There is no need, absolutely right. So, but look at the term here. So this lambda, one term is lambda and the other term is square root of lambda square minus omega naught square. So obviously now lambda would be definitely greater than square root of lambda square minus omega naught square. So this is certain positive number. This lambda itself is a positive number, but greater than this. So eventually, if you look at the alpha value, so alpha would be less than 0 here because this is positive, this is more positive. That's why alpha 1 is definitely less than 0 here. Look at the alpha 2 here. So alpha 2, this is positive number, this is positive number, negative sign. So this definitely will be less than 0. So what happens here? So from this, the first solution, so basically our x of t is a linear combination of two functions. The first one, e raised to alpha 1 t. Now alpha 1 being less than 0, this is decaying in nature. And similarly, alpha 2 as well being less than 0, negative, this is also decaying. So our amplitude is going to decay, and due to higher damping, so our damping is comparatively very stronger, so eventually it will die out very soon. So the solution will look like, so let me call this solution as x of t. So this would, I'll simply write as alpha 1 t. So let's put some constant here, plus b times alpha 2 t. And this both e raised to alpha 1 t and e raised to alpha 2 times t would be decaying in nature. So if I look at the graph of the solution, let's say this is displacement, so this is time axis. Now, depending on the nature, so as our damping force is larger, this is called overdamped oscillations. This is called overdamped oscillations. Why overdamped? Because your damping is much stronger than other forces, right? And if you look at the solution of the displacement, both of these functions are decaying, one alpha 2, one corresponding to alpha 2 being very negative, it is decaying even at faster rates. So if I look at the solution, so our solution, so first of all, suppose if my displacement is starting from 0, so first of all it will grow, but if you look at the solution, there is no oscillating term inside this solution. Like in our previous case for the underdamped oscillation, we have a sine term, sinusoidal term, and a decaying term. That's why our sinusoidal oscillations were kept oscillating between this decaying function. But here we don't have any sinusoidal or periodic term here. We just have the decaying term. So eventually, as time proceeds, this displacement will decrease without being oscillating. So it will eventually come to 0 as time proceeds. So this is called overdamped oscillation. This is called overdamped oscillations. And what is the example of this? So you know the automatic doors. Automatic doors. So if you push the doors, initially it will just close to closing the door, but as it is about to close, it will slow down, right? So this is the displacement. Initially it is more, than at the closing time it is eventually going to 0. So the displacement basically decayed, and now it is going to 0 as time proceeds, and it will slowly close, right? So this is the example of overdamped oscillation. And from this, you'll be able to write or uh, identify the nature of this displacement. And the important thing for this overdamped oscillation is the solution displacement field is not going to be oscillating, right? So it will grow and eventually decrease or die out as time proceeds. Okay, so let's move on to the third type of damped oscillation, in which lambda square is equals to omega naught square. So this leads to b square equals to 4mk. And this condition is known as critical damping. This condition is known as critical damping. So what does it mean basically, critical damping? So if you look at the solution, alpha 1 is equals to minus lambda plus square root of lambda square minus omega naught square, and alpha 2 is minus lambda minus square root of lambda square minus omega naught square. So this term basically is going to 0. Similarly, this term is basically going to 0. So if you see here, your alpha 1 and alpha 2 are same. But remember the differential equation from where you started. It is d2x over dt square plus 2 lambda times dx by dt plus omega naught square x. So this is basically 0. This is basically 0. So might have I forgotten, I'm not sure, this x somewhere. But remember this differential equation d2x upon dt square plus 2 times lambda times dt dx by dt plus omega naught square x is equal to 0. So here, if your alpha 1 and alpha 2, which is a solution by taking our x of t as a e raised to alpha t in general, now our alpha 1 and alpha 2 are becoming equal. So we end up having two solutions, alpha 1 and e raised to alpha 2 times t, which are same. But this is being second order differential equation. We must have two linearly independent solutions. So let's not go again into the details of solving ordinary differential equation. And in this case, in such cases where the solution is repeated, we have to consider one more solution. And this looks like, the first solution looks like some constant e raised to alpha 1 times t plus b times, I'll multiply this with a t e raised to, I'm writing alpha 1 2 times t because alpha 2 is equal to alpha 1. So what it looks like, so this is, I will write as, so here alpha 1 and alpha 2 are basically minus lambda. So I'll write this as e raised to minus lambda times t, a plus b times t. So the solution for this displacement field in case of critical damping, where this lambda square has become equal to now omega naught square, the natural frequency square. So in that case, there'll be a decaying term, but there'll be a time dependent linear term as well. And now if you look at the graph for the displacement versus time. So this is time axis, this is x of t displacement. So again, if you look at the solution, there will be a decaying term, e raised to minus lambda times t, but there is no periodic term, right? So similar to overdamped oscillations, we don't have any oscillations in the solution. So if I start from 0, it will keep growing, and eventually as there is a decaying function, it will die out. And probably as compared to the overdamped oscillation, it will die out quickly due to this linear term. So because of this term, my oscillations are dying out quickly than overdamped oscillation. And this is known as critically damped oscillations. This is known as critically damped oscillations. So what is the best example of this? So you must have seen the ammeter and voltmeter pointers, right? So suppose the current is flowing through circuit. So it is showing certain value inside your ammeter or voltmeter. And if you suddenly switch off the circuit, so it should go to the equilibrium position as quick as possible. And remember, while doing this, it should not keep oscillating, not even for a longer time, right? So if the pointer is pointing at certain point, and now eventually as circuit switches off, if it comes back to the equilibrium position, so while coming from this to equilibrium position, it should do this very quickly and it should not keep oscillating. So what happens if I use underdamped system for this? So if I use underdamped system, it will come out to this, it will come back to this equilibrium position. But remember, in underdamped system, it will decay, the displacement will decay, but over a longer period of time. And while doing this, it will keep oscillating. So that is not what is desired here, right? So what happens if I use overdamped oscillations? Again, no doubt there will be no oscillatory motion, but compared to this critical damping, overdamped oscillations will take longer time to decay out the amplitude. So again, so it's better to use critical damping than overdamped system, right? So that's why in these examples, we use critically damped oscillators. So in a nutshell, let's revise this particular thing. So we have looked at the differential equation, which looks like basically we started with this m d2x over dt square. This is inertial term plus b times dx by dt, which is resistive force, plus kx restoring force equal to 0. From this, we have written this down d2x over dt square plus 2 lambda times dx by dt plus this omega naught square times x is equal to 0, where this lambda is basically b over 2m and this omega naught square is k over m, right? And for finding out the solution of this differential equation, we have considered our solution as a times e raised to alpha t in general. And based on different conditions, so we have ended up with alpha 1 comma 2 looking like minus lambda plus minus square root of lambda square minus omega naught square. So depending on the values inside the square root, if lambda square is less than omega naught square, it is going to complex region. So it can be represented by using sine and cosine functions, and there'll be exponential of this negative term. So there are basically two terms. One is exponentially decaying and other is oscillating. So that condition is called underdamped oscillations. So the first one, lambda square is less than omega naught square. This is underdamped oscillations. The second one, obviously, then lambda square greater than omega naught square. So lambda square greater than omega naught square, positive number, but not greater than lambda. So that's why alpha 1 and alpha 2 both are negative. And if you look at the solution, both terms are exponentially decaying. So there is no oscillating or periodic term in this particular solution. So it is only going to decay. So this is called overdamped oscillation. So in underdamped oscillations, your damping resistive force is comparatively smaller than other forces in the system. In overdamped, look at this lambda. Basically, it is directly related to damping constant B. So it is more dominant in case of overdamped. And the third obvious case is lambda square is equals to omega naught square, which is referred as critical damping. This is referred as critical damping. So this is how we looked at damped oscillators and its types based on this particular value inside the square root by looking at the solution of the differential equation for the damped oscillations.